Hello, this is Mr. Collier, and today we're doing some curve sketching. So here, let's look at the first derivative test and the second derivative test, and you can read most of this yourself. It's going to fix a small error here. If f prime of x is less than 0, then yes, the function is decreasing, and if it's greater than 0, yes, the function is increasing. Now, if it's equal to 0, there is a horizontal tangent, but you cannot determine actually if it's increasing or decreasing or neither. Could be either of these three cases, so please cross this out. That's not quite accurate. So that's the first derivative and first derivative test, and here's the second derivative test. You can read those yourself. Let's go to number 2. Sketch a graph given the following information. Now here's your domain. Okay, we have some limits, we have all kinds of stuff. So looks like our y values we might need to go up to 3 or so. 1, 2, 3. X values maybe up to 4. 1, 2, 3, 4. Let me just space that a bit better. Try to be a bit more accurate. Something like that. Okay, f of 1 equals 3. F of 3 equals 1. Let me go to red, sorry. Limit as x approaches 2 from the left of the function equals infinity. Okay, so approaching 2. That would seem to mean there's going to be a horizontal asymptote at x equals 2, or a vertical asymptote, and the function is approaching infinity, so it's kind of going up this way, I think. We'll see if that makes sense with the rest of the information. And it's also approaching infinity from the right, so we have some situation like that. Alright, and the limit as x tends to infinity of f of x equals 2. We'll get to that in a second. That looks like actually a horizontal asymptote. Right, and let's just kind of draw that in here. This is y equals 2, so it's approaching 2. So now we're talking about first derivative and second derivative stuff, so I like to just draw on the bottom a row for first derivative and second derivative. Okay, so it says, so this is the domain of the entire function, so it's not defined at 2, so obviously there's going to be a vertical asymptote, and we're only looking from here onward, and it goes off to infinity. Alright, now it says here the limit as the function tends to 0 from the right is negative infinity. So that should mean that this is also a vertical asymptote, and the function is going towards negative infinity. The y values are approaching negative infinity as you get closer and closer to 0. So we have this situation. We have, alright, so let's take a look at this. At 1, we have the derivative, the first derivative is 0. At 3, we have the first derivative of 0, so those are possible maximums or minimums or points of inflection. At 1, the second derivative is 0, so it's not positive or negative. That's probably a point of inflection. So let's take a look. So the function is probably going like this, oops, and then going off to infinity here. Okay, that shouldn't look like a point of inflection. I'll try to make that a bit smoother. Okay. Something like that, although, yeah, something like that looks good. Alright, so the second derivative at 4 equals 0, that's possibly another point of inflection. Oh, okay, here's more information about the second derivative. So it's concave, it's negative here, so it's concave down between 0 and 1. Concave down between 0 and 1. and between 4 and infinity it's concave down, and in the other two intervals is concave up. Okay, so that tells us, I think, all we need to know. Okay, so actually we also have first derivatives here and here are 0. So that looks like a point of inflection. We'll see now. So the concavity changes here. So yeah, we do have this point of inflection. Okay, which makes sense. Here the first derivative is equal to 0, but it's increasing over the whole time. So this is positive and this is positive. And here we have concave up. And we have this point right here. Actually, let's adjust that. And it's concave up the whole time. At this point here, it changes concavity. So we're concave up, and then all of a sudden we're concave down. And that shouldn't touch y equals 2. It just approaches y equals 2. Okay, so the concavity changes to concave down. From concave up to concave down. So that's a point of inflection. We have a horizontal asymptote here because it's approaching 2. So yeah, this matches. See here we have f prime of 3 equals 0. We have a minimum here. Alright. Then the concave, because the concavity stays concave up. So this is the required graph. Okay, so next, these are some steps that we should use when we're sketching a graph. Now this one's going to be a little bit trickier than the previous one. So analyze and sketch this graph. We are going to need to find the first derivative and the second derivative. Alright, now first of all, maybe we can note that sine of 0, sine of 0 equals 0, so we do have the point 0, 0 on the graph. Alright, and let's go ahead and find the first derivative, I suppose. So the first derivative is equal to, using the product rule, e to the x sine x plus e to the x cosine x, alright, which equals e to the x outside of sine x plus cosine x. So when that equals 0, we have, well, e to the x can never be equal to 0, so we have sine x plus cosine x equals 0. To solve an equation like that, we divide by cosine and we get tan x plus 1 equals 0, and tan x equals negative 1. So let's find the x values at which tan x equals negative 1. If you look at this, tan is negative here and here, and we're looking from negative 4 to 4. So the possible x values could be here, which is 3 pi over 4. Now let's look at the number 4. That's a little bit bigger than pi, so we can consider values bigger than pi, but tangent's positive here, so there's nothing over here. There's no more positive values. So if we look at negative angles, up to negative 4, then here we're going to have an angle in this region. Okay, that angle is going to be negative pi over 4. And let's look at when we get up here. So this is negative, negative, negative. This is negative pi, which is negative 3.4. If you go to negative 5 pi over 4, that, if you use your calculator, is actually negative 3.96, I think. So it is within our domain, so we have to consider that one too. So there are 3 critical values. Okay, and these are going to be our possible maximums or minimums, maybe points of inflection. Alright, so let's do the sign diagram for these points right now. 1, 2, 3 critical values. We have x and we have f prime of x. So let's put them in order. Negative 5 pi over 4, negative pi over 4, 3 pi over 4. The derivative is 0 at these points. So what happens in between? Now in here, between here, you obviously have 0. So if you plug 0 into the derivative, you get sine of 0 is 0, cosine 0 is 1, so we have positive derivative in that region. Bigger than 3 pi over 4 would be like pi. If you plug in pi, you're going to, well, this is going to always be positive, you don't have to look at that. Sine pi is 0, cosine pi is negative 1, so it's negative. And this region, in between these two values, we have negative pi. Sine negative pi is 0, cosine negative pi is negative 1, so it's going to be negative. And if we look at here, now we don't want to, well, I guess we could go, even though it's not in the domain, we could look at negative 6 pi over 2, which is negative 3 pi over 2, which is here. So cosine is 0, sine is 1, so it's positive. Okay, so this is going from increasing to decreasing. Right, so we're going to have a maximum, decreasing, increasing, so we're going to have a minimum, and then we're going to have another maximum. Okay, so that is a max, and this is a min, and that's a max, and that'll help us with the graphing. We also will need to find the second derivative to find any points of inflection. So second derivative equals, if we use the chain rule on the first derivative, maybe this version, we get to e to the x sine x plus e to the x cosine x plus e to the x cosine x minus e to the x sine x. And two of those cancel, and we get second derivative equals 2 e to the x cosine x. Okay, so setting that equal to 0 to find our possible points of inflection, we get, now e to the x can never be 0, so we're just going to get cosine x equals 0. We have to solve that. So where does cosine x equals 0 between negative 4 and 4? That's going to be at pi over 2 and negative pi over 2. Okay, so if we look at, so pi over 2, if we look at 3 pi over 2, then that is actually going to be too big. So there's only 2 possible points of inflection. So let's do a sign diagram for that. So we have negative pi over 2, pi over 2, x, second derivative. Between that is 0, so cosine 0 equals 1, so we're going to get a positive number in between there, positive second derivative. And then bigger than that, something like cosine pi. Cosine pi is negative, and over here cosine 0 is, oh, not cosine 0, sorry, cosine 0 is in between. Cosine negative pi will give me a negative cosine. So here we go. So we do have 2 changes of concavity. We do have 2 points of inflection. So these are both points of inflection where the concavity changes. We have concave down, up, and down. Alright, so let's sketch the graph over here. That's not very straight at all. Alright, so let's just use that. Alright. Okay, that's a bit better. better. Okay, that's 4. Let's go 1, 2, 3, 4. 1, 2, 3, 4. And yx. Okay. So we saw zeros on the graph, so let's plot that one first. It's often an easy point to get. And let's put in our maximums. We have 3 pi over 4 is over here, I think, somewhere. 3 pi over 4 is about, I think, a little bit less than 3, so here's a maximum. And our minimum is over at negative pi over 4, which is less than 1. I think our minimum is right about there. And we have another maximum over here. Alright, it's very close to 0. And point of inflection is at negative pi over 2, which is about negative 1.5. Let's put a point of inflection green so we know the difference. We have another point of inflection over at pi over 2, which is about 1.5. Okay, and yeah, I think that's all we need to graph this thing. So I'll graph in yellow. Let's do that. So the function is between, well, here we have, between here and here, which is right here, we have the function is decreasing and the concavity changes. So something like that. That shouldn't be too high right there. Let's try that again. Okay, so it's concave up, and then it's concave down according to this. And then after from pi over 2, it's concave down. Okay, I don't know where it goes. And in between here is concave up, and it changes concavity here. So this is what it looks like, and you can label some of these points as well. Like this is 3 pi over 2, for instance, whatever the y value is. Okay, so there's what the function looks like. Let's take a look at Desmos to see what it looks like. And this is kind of what it looks like. You can see there's a change in concavity over here. There's a minimum, there's the maximum, there's another change in concavity here. So it kind of matches what we drew. Suppose we could have got an x-intercept, so we could have plotted that a bit more accurately. But we plotted all the maximums and the minimums and the points of inflection fairly accurately. Okay, without a GDC, analyze this function. Now to analyze this, first of all, just note that this is not defined for all x. Alright, so this is only defined when the argument of the natural log is positive. Okay, so sine x has to be greater than 0. And we can see here, so that means sine x has to be positive. Sine x is only positive between, well, let's write down the domain, between 0 and pi. Okay, or if we go all the way around, we get to 2 pi, then 2 pi to 3 pi. And then we go around again and we have 4 pi to 5 pi, and so forth. And we can do the same thing, similar thing in the negative quadrants as well. Okay, so I'll put a dot 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 there. So there's big chunks where it's not defined. So we'll have to remember that when we do our graph. Alright, so let's look at, well actually let's look at the range first. So if we look at the range, notice the argument ln is sine. So this is going to be any, so the maximum that sine can be is 1. So we're just going to go up to this part of our sine graph. Okay, you're only going to get y values between infinity and 0. Okay, so only this part of the function. Alright, so we got a domain and range. Let's do the first derivative. The first derivative equals 1 over sine x and chain rule cosine x. Okay, which equals cosine x over sine x, or cotan x, maybe that'll help us later. The second derivative equals, well, that's going to be, the second derivative of cotan is negative cosecant x, which is negative 1 over sine x. Alright, so let's see what happens when the first derivative is equal to 0. Then we have cosine x over sine x is equal to 0, and that's only 0 if the numerator is equal to 0. Okay, so we have x equals 0 at 2 pi, or pi over 2. And because, remember, it's only defined here, not down here where sine is negative. So we have pi over 2. We'll skip this one, and then we'll go to 3 pi over 2, or 5 pi over 2 when we're back up there on the y-axis. So 5 pi over 2. So 5 pi over 2, and then we skip 7 pi over 2 because that's not in the domain. That's 9 pi over 2, and so forth. So you can actually even make an equation for those. It's 4k plus 1 over 2. That's how we can generate them. Pi, k is an integer, right? So there's an infinite number of them. Those are possibly maximums or minimums. Let's check the sign diagram. So x, f prime of x, pi over 2, and 5 pi over 2. Okay, so then, well, let's just check the pi over 2. They'll all be the same after that. So bigger than pi over 2, we have, well, let's just look at this diagram again. If we have a larger angle than pi over 2, then we're in this region, and cosine divided by sine will give you a negative number when you have a bigger angle, right? When you have a smaller angle, they're both positive, and you get a positive number. And that's going to work for all of them. You're going to get, so you're going to get increasing and then decreasing, so we have a maximum. Okay, all of these are maximums. Let's look at the second derivative now. Let's just pop back up to the second derivative. So this is looking at the second derivative, and remember our domain. Our domain is just here, right? So sine is always positive. That means our second derivative, because it's negative 1 over sine, is always going to be negative or less than 0. So that means everywhere on the function is going to be concave down. Concave down. Okay, given this information, we can now start graphing the function. Our critical values, our maximums are at pi over 2 and so forth. Now if you look at our function, like g of pi over 2 equals ln sine pi over 2, and pi over 2 is 1, so it equals 0. Okay, and it's going to be the same with all the maximums are going to have y values of 0. So to graph the function, let's go up in multiples of pi over 2. It's pi over 2, pi, 3 pi over 2, 2 pi, and so forth. So this is pi over 2, and remember sine is equal to 0 here and here, so we're going to have asymptotes there where the function is undefined, or actually we're going to have big chunks of where the function is undefined. So anyway, we're going to have asymptotes here. This is a maximum. Remember, it's always concave down, so the function is going to look like that. is not defined in this region. Okay? And then we have a 5 pi over 2. And then we have another asymptote. Here's the maximum, concave down, and it goes on like that. Okay, we're going to have another section like that over there. It works the same way going back here. We're going to have pi degrees with nothing because it's undefined there. Then we're going to have a maximum. Then we're going to have another vertical asymptote, concave down, so it looks like a bunch of, sort of like a parabola, but not actually parabolas. So that is what the graph of the function looks like. And let's take a look at the Desmos version. So that's what the Desmos version looks like. So it looks like our graph is correct.